Welcome to our series on thermochemistry, and today we're going to be looking at heat of reaction. Before we progress to heat of reactions, first of all, let's remind ourselves what heat is. Heat is the transfer of thermal energy from one body to another by virtue of a temperature gradient. That means moving from an area which is warm to an area which is cooler. There are two symbols used to represent heat. One is Q and the other is H. H is equal to Q at a constant pressure. And many of the chemical experiments we carry out in the laboratory are done at a constant pressure. So when we have heat at a constant pressure, we call this H enthalpy. A reaction in which heat is taken in is considered endothermic, and enthalpy, or delta H, is positive. In the example here, I have water, which is a solid, and heat is added so that it becomes a liquid. And we can see enthalpy, delta H, is 6 kilojoules. This indicates the fact that enthalpy is positive indicates that heat was absorbed. A reaction in which heat is given out is exothermic. Delta H, or enthalpy, is negative. In the example below here, I have water in the liquid form going to a solid form. We can see that delta H is equal to -6. It's exothermic. Heat is given off, so heat is lost as it goes from a liquid to a solid. Another interesting thing to note is that when it's endothermic, when we go from a solid to a liquid, delta H is 6 kilojoules, but when we go from a liquid to a solid, it's -6 kilojoules. So that brings us to the law of Lavoisier and Laplace, which says heat of the forward reaction is equal but opposite in sign to the heat change for the reverse reaction, which is what we just saw. So when solid water, which was ice, went to liquid water, it was 6 kilojoules. However, the reverse reaction of going from a liquid to a solid was -6 kilojoules. So it was equal in magnitude but opposite in sign when the reverse reaction takes place. So let's define heat of reaction. Heat of reaction is the heat released or absorbed when the number of moles of reactants in a balanced equation react completely. In the example below, we have H2O and the solid, which is broken down into its unit components of hydrogen and oxygen. To do this, we can see enthalpy, delta H, is equal to +286 kilojoules per mole. So it absorbs energy in order to break the bonds of water to form hydrogen and oxygen. So how do we measure heats of reaction? Well, there's a very simple, what we call the polystyrene cup calorimeter. And here's how it would work. Let's take 50 centimeters cubed of 1 molar solution of HCl and place that in one polystyrene cup, and we'll take the temperature. In a second polystyrene cup, 50 centimeters cubed of a 1 molar solution of NaOH is placed in there. The initial temperature of both your acid and your base should be the same. Ideally, they'll both be room temperature. Then you will add the base to the acid in the polystyrene cup, and you will stir with the thermometer. Typically, a lid would also be placed on top of this solution to prevent the loss of heat. The maximum temperature is then recorded, and the heat of reaction is then calculated. So here's a diagram of what you would have in the laboratory. Here is your polystyrene cup. Polystyrene, as we know, is a good insulator, and it does not allow the transfer of heat between the system, which is your solution, and the surroundings, which is the laboratory. We have our reaction mixture of our acid and base in here, and we have the thermometer recording the temperature of the reaction mixture, and we also have our lid to prevent the loss of heat. So to calculate the heat of reaction, we firstly look at our chemical reaction and we check that it's balanced. So here we have HCl plus NaOH goes on to form NaCl plus H2O. The equation is balanced. Now I have a look and see what products are in my reaction mixture. I have NaCl, which is a salt, but the solution is mainly water. We can see here H2O. The equation for calculating heat change is Q is equal to M times C times delta T, where Q is heat, M is the mass, C is the specific heat capacity, and delta T is the temperature change. Because this reaction is done at a constant pressure, we can say that Q is equal to delta H, enthalpy. So our equation changes to delta H is equal to M times C times delta T. For our mass, we added 50 centimeters cubed of acid and 50 centimeters cubed of our base, and they collectively made water. So we will have 100 centimeters cubed of water. We know that 1 centimeters cubed is approximately equal to 1 gram for water. So we can now change our volume to a mass. So 100 centimeters cubed is approximately equal to 100 grams, which we then change to kilograms, which is 0.1 kilograms. For C, which is my specific heat capacity, I look at what is in my solution, and it's water. Thus the specific heat capacity for water is 4.2 kilojoules per kilogram per degree C. My temperature change, so from our laboratory, our initial readings, let's say, of our acid and base was 10 degrees C. The temperature change then for the reaction mixture went up to 17 degrees C. So the difference, so T final minus T initial, which would be 17 degrees minus 10 degrees, gives me a temperature change of 7 degrees. This is my delta T. So delta H is equal to 0.1 kilograms multiplied by 4.2 kilojoules per kilogram degree C times 7 degrees C. Let's cancel out our units to see what our unit of measure is. So I have kilograms and per kilograms. They cancel out. I have degrees C and I have per degree C. They cancel out. So the only unit of measure left is kilojoules. So I now multiply my 0.1 times 4.2 times 7, and when I do, I get 2.940, and my unit of measure is kilojoules. Have a go at this one yourself. Calculate the heat of reaction when 30 centimeters cubed of 1 molar nitric acid, which is HNO3, is added to 30 centimeters cubed of 1 molar potassium hydroxide, which is KOH. The temperature increased by 5.5 degrees C upon reaction. You're then given the chemical equation. We check that it's balanced, and once it is, then proceed. So pause the video, have a go, and as always, the answer is on the next slide. So the calculations for that problem are as follows. To calculate the heat change, Q is equal to mc delta T. Because the reaction is done at a constant pressure, Q is equal to delta H. So delta H is equal to mc delta T. Delta H is equal to, our mass is 30 centimeters cubed for our acid plus 30 centimeters cubed for our base. That reaction mixture then forms water. So we know for water that 1 gram is approximately equal to 1 centimeter cubed. So we can convert our volume into grams. We then want to convert that then into kilograms. So 60 grams is equal to 0.06 kilograms. I need the specific heat capacity of that reaction mixture, which is mostly water. The specific heat capacity of water is 4.2 kilojoules per kilogram degrees C. The temperature change we were told was 5.5 degrees C. So my calculation should be 0.06 times 4.2 times 5.5. And delta H is equal to 1.386 kilojoules. So that's it for heats of reaction today. In the next presentation, we will look at heat of combustion. Thank you for joining me.